So first of all, thank you for attending, and lovely to see you, Edric. And how do you pronounce your full name?
It's Matwiejew.
Oh, that wasn't how I pronounced it. Are you sure you've got it right?
I am not. It's a German spelling of a Russian name.
Oh, wow.
I've been told. And the only people I've met who have been able to pronounce it are either German or Russian. Unfortunately, I'm neither, so I just have to get by.
Well, I have to say, I actually, I don't know whether you're used to English. We have O levels and A levels. O levels is when you're 16, and I have an O level in Russian. Yeah. It's a great language because it's phonetic. It's relatively easy to learn because phonetic, means it's spelt as it sounds rather than the ridiculous way England carries on. And there's no verb to be. So it's a little bit like a Red Indian. You, there, mouse, table. You work out the rest. So
straight to the point.
Yeah. So can you say it one more time?
Matwiejew.
Matwiejew. Oh, well, I'm getting better. Matwiejew. Okay, well, look, thank you, Edric, for agreeing to do this interview where I will record this and put it up on the Kwekwa website. And I know there's a lot of young students who want to see this because I've been telling them about how interesting it'll be to hear a real, PhD candidate. I'm not exactly sure what your full title of your PhD, but I'm sure you'll tell us. And it's very interesting to hear your viewpoint. It's very interesting to hear how you got there and what opportunities, commercial and otherwise, are open to you. And I'm sure we'll get onto that very shortly because it's such an exciting time.
I think we're going to undergo a change that's maybe, far more significant in terms of the scope of problem we can solve. But it's going to be very interesting spotting it as it rolls out because, the first information revolution, we had computers in our homes, cell phones in our pockets. And I think a lot of that's going to look quite the same materially, but there'll be, I think, a lot of very interesting run-on effects, which I'm sure we're going to get into.
I can't wait for us to get there. I know we will. But look, let's start with your background. So if you can tell me pre-university days, what was life like for Edric? And were you clever as a child, or not so much?
Well, if we want to go all the way back, I guess I'd say that I'm lucky in that I've always been interested in science, and that's not entirely to my own credit. It helps that my dad was a chemist, and like a lot of young boys, when you're very young, you want to be like your dad. So that was something that always interested me, but I was a very distracted student. So I don't think some of my teachers would have slated me as being a PhD material at various points in my school life. But I guess I'd stick with that kind of, curious and always wanted to be learning about something, tinkering with something or reading. But I wanted to do it my way.
Which is a very, very good thing. Did you go to school in WA?
I did, yeah. So I went to school in WA, back to a place that's just around the corner from here. And then I've wound up all the way through to university, also doing university in WA, which, given the state of the world at the moment, has worked out relatively well for my PhD, I have to say. But yeah, I've been very fortunate with the opportunities that I've had here in Perth, and it's allowed me to continue to move forward with my, I guess, academic and career goals, while also being able, to be around friends and family and all of that stuff. So I'm very fortunate in that regard.
Well, I think we make our own fortune, but well done to you. So, what degree did you do at university? So, how did you do TE-wise, and then what degree did you do before you got onto your PhD journey?
Well, I guess one thing I would say is I feel like I am evidence that of your TER or ATAR or whatever those initial tests that students take now. I think I am an example of that not being the most important factor. I, as a 17-year-old, so now a long time removed from wanting to be like my dad,
Yes.
had thought that I had no interest in pursuing something that was related at all to mathematics. I was really into film and recording music, and I just wanted to leave school and try to make art. And that's what I tried to do. So I was fortunate again, it's a combination of work and luck that my grades were okay. I had enough to get into university with my media grades, basically. And I did 2 years of a film and music degree before receiving what was some of the best advice I think I ever received from a lecturer, which is, if you feel like you have gotten what you need to get from this course to go out and start making music or start writing scripts, start making films, you should go and do that. Don't waste your time sitting in a classroom if you feel like you have all of the tools that you need. And while, like, at this point, strongly argue for the efficacy of a good university education, but at that point, I made that decision with a friend of mine, and I spent the next few years trying to do those things. And it's in that world that I eventually stumbled back into my interest in the sciences.
While you were doing film and music, what if I'd have said to you that you would soon, be studying quantum computing?
I think I would have been quite excited and very daunted. It's definitely something I've worked my way up to, I suppose I would say. It's not even something I thought I would necessarily get into the time of my undergraduate, graduation. Let's see, I would have graduated around 2016. So quantum computing at that point is a fairly exciting thing. There's a lot of buzz.
Yeah.
But over the last few years, I would say it has just shot off astronomically. Yeah. So I think I kind of entered the space when there was already a lot of excitement. I have sort of learned about it, gone through my master's and started a PhD during a period where it has just exploded. The thing that I was really interested in was simulating molecular systems. So when I eventually went back to university after actually working as a lab technician for a while, because it turns out that, making art doesn't pay too well, unfortunately.
No.
So I had to do something else that would interest me. So I started working in a small laboratory. After working there for a while, I decided to, head to university because I just really enjoyed speaking to physicists. Whenever I met a physicist through my work, we had a great chat. So I enrolled in a double major in chemistry and physics.
Oh, right.
And to get into that, I had to go through an extra year of bridging courses for my mathematics. And in fact, I got almost a year shaved off, fortunately, because I technically would have had to do additional introductory material. But what I did is I went and spoke to one of the course coordinators and just talked to them about where I was at mathematically, because I had been picking up things here and there over the years and I was interested. So I was able to demonstrate through a conversation that they should let me into the next course. So I guess that's one message or something I would like to mention as well, especially if you're an older student going back to university, feeling like you can send an email to a course coordinator when you're looking at getting into a course and trying to arrange meeting time to see whether or not it's a good fit for you. That is something you can do. And I think a sign of a good course is one where people will make a small amount of time for you. So that's how I got into my chemistry and physics, I guess. I enrolled.
That's excellent
and I
advice.
really wanted to push myself, really. And that was the main decision. I wanted to push myself. I wanted to be in a room with other people who I found interesting, working on problems that I found interesting. Like when I was writing music or playing in bands, it was about being in a room with like-minded people, working on art that I was motivated to, produce. And now when it comes to research, it's the same thing, but it's like a different goal, different tools. But again, it's about that collaboration and that feeling of solving a problem, I guess.
Yes, and creating something.
Mm.
Again, when was the first time you heard the phrase quantum computing?
So we know that like Richard Feynman gave a talk. What was it like? There's a lot of room at the bottom, or
yes,
something like that. There's a lot of stuff we can do at the smaller scales, where he kind of introduced the idea of quantum computing to a sort of popular audience. I don't think he was the first to do so, but he was one of the first. So I encountered that, and then so I'm aware of it. But as I was going through my undergraduate course, I did become aware of a research group at UWA. So that's the research group led by Professor Jingbo Wang.
Yeah.
And current name that we go under is the Quantum Information Simulation and Algorithms Research Group, so QISA. And you would see I'd go to afternoon teas where people were presenting their research, or take a look at the available master's research topics as I was thinking about going to postgrad, and this kept on appearing. And I liked that it was using physics to do computing, so I'd get to use some of my quantum mechanics, learn some programming at the same time, and then maybe it would help to simulate molecules, because that was a problem that I was really interested in through my chemistry. The idea of being able to, solve for the structure of a protein, or a type of new type of energy storage, that kind of thing. So I began to see bits and pieces of that research, and in particular, research around algorithms that are centered on these things called quantum walks, which as an undergraduate, where this quantum mechanics and research in quantum mechanics is this very scary, almost like unattainable place to kind of even reach, because even by third year, like master's student or honors student, hearing about their projects, I'm not even sure what they were talking about. But there was this concept of a quantum walk, and I felt like I could get what that was, because it had this really nice visual depiction. And I think that also drew me towards it.
Excellent. Look, now you're talking about quantum walks. Okay, so, well, tell us exactly what a quantum walk is and what it's useful for, what its application is.
So a quantum walk is the quantum counterpart to a thing called a classical random walk. And what we mean in mathematics and physics, when we talk about a walk, is we're talking about some object moving through space as a function, say, of time or number of steps. So we might consider a random walk, where we have a walker on, say, a grid of points, so possible positions, and at every time step, it can choose to go in, say, one of four directions. And we can look at its evolution with time. So it sort of moves around the possible space. And we make use of random walks in classical computing, say, to sample complicated functions or areas. So you can, start off in one sort of point in your state space and kind of move around it and look at how properties change in your system. And in that sense, kind of get like a statistical sense of how it's all built up. Now, We can do the same thing quantum mechanically, where again, we're considering again some space. We would usually think of them as again like these like discrete, so very definite little points, and a walker in that space that moves across it. But because we're dealing with quantum mechanics, we bring in a few novel, I guess, effects. So we have firstly superposition. So that's the whole idea of a quantum state being able to exist in many of its possible configurations at the same time, and also interference and entanglement. So not only can it exist in a state of superposition, it can interfere with itself. So if one quantum state has a high probability of being here, but another state has a very low probability of being in the same spot, they'll cancel out to a net zero probability. So unlike a classical random walk, where if you're thinking about a random walk along a line, and we start off in the center, and then we kind of wanted to plot, on average, where is our walker? We'd see a distribution that looks something like that, like our standard bell curve.
Yeah.
If we did the same thing on our line with a quantum walker, we actually see this really kind of interesting, and I'd say almost a little pretty interference pattern, this kind of oscillating wave, which is the walker self-interfering with itself. So it's really different behavior.
It is, isn't it?
And
so the random walk, that's a Monte Carlo simulation?
Yeah, I believe so. So you could formulate or conceptualize of a Monte Carlo simulation as being a random walk, because you're starting in a particular state, and then you're kind of evolving through a system using this sort of statistical sampling of your state space.
Yes.
So that is an instance of that. And we also maybe would be interested in using a random walk to model a physical system. So say if you had a particle that is really energetic, say like a hot gas particle. If we're thinking about the, the ball and stick model of molecular dynamics, you could model its path through state space, through space as a random walk. If it's, encountering enough barriers to kind of disrupt its motion in one direction, I suppose.
Is this like a dispersion of a gas and Brownian
motion? Yeah. So you could, exactly. So dispersion of a gas, that would be another instance. Kind of like any instance where maybe starting off at one point, and then as it kind of diffuses, so it's a diffusive kind of propagation, you wind up with that kind of broadening of the peak, and then almost bell curve normal distribution. So we would say that a random walk is, in general, it's a dispersive evolution, or it propagates in a dispersive manner.
Yes. And the higher the sample, the more dispersed it will be. So it will be the confidence levels and the actual, I can't remember what it's called, but the probability density will be narrower, won't it? The more you have. But I'm really interested.
So just on that, I think just because it'd be useful when we get to the quantum world, is that we could talk about the location of a random walker, and again, thinking in terms of our line, it's only ever going to be in one particular point. If we just think about that walker, it gets interesting when we start to think about the distribution of the walker over time. So where is it likely to be if we look at the system multiple times?
In the classical world,
that's where it starts to get more interesting. It's just, if we sample a random walker on a graph, it'll just be somewhere. But if we start asking, where is that somewhere in relation to where it started, and we measure it multiple times, then we start to build up these probability distributions. And well, I suppose we'll get to the quantum side of things
I don't know, can you see the questions, Edric?
Sorry, I'll bring them up.
There's just one from Tom, which is a goodie.
Yeah, so Tom's asking if we could use a random walk method to determine the interference of qubits against each other and the level of error in computation. So you could model it as a random walk, like as this kind of dispersive evolution. In fact, there is a type of quantum walk called a quantum stochastic walk, which incorporates a classical random walk and a quantum walk that was coding a simulator for these quantum stochastic walks. Was one of the things I did in my master's. You can use that to model, say, a noisy quantum system, so say a noisy collection of qubits.
Wow, I mean, that's like an oxymoron to me, saying quantum stochastic.
Exactly, yeah. So it's a combination of quantum dynamics with stochastic, we'd call it classical scattering.
Yes.
So like you could think if you have your nice quantum system evolving with all of its beautiful dynamics, and every so often the classical world intervenes and just scatters something somewhere and ruins your coherence.
So can you explain again the difference between a random walk and a quantum walk? I love the way you were saying, yeah, I mean, the random walk is famous for its bell curve, and you can then make decisions. I mean, if I can equate it to which it's used for a lot, stock portfolio optimization.
Mm-hmm.
So there's, so like pricing options and things like that, there are many different possibilities, and by using random figures, you can find out where the mean is. What I can't understand is what is the benefit from a quantum walk? How will the quantum walk affect being able to optimize stock, for example, or will
so that's a really good question. So, we've got this quantum walk and it behaves differently. So destructively interferes with itself, has superposition, and you get these really beautiful looking probability distributions if you look at them plotted out over a graph. But it turns out that, there's actually some really, cool things that are happening as a result of that.
Wow.
One of them is that on certain graph structures, so now we're moving sort of to a more concrete sort of description of the state space of our walker. So previously I've mentioned we have these points and it can move through these points.
Mm-hmm.
Now we're considering a collection of points or vertices connected to each other by edges. And for those who like to think mathematically, you could represent this as a matrix, a symmetric matrix of zeros and ones. So you have the rows for each, a row for each vertex and a column for each vertex, and then ones at say 1, 2 and 2, 1 means that we have a connection between those two vertices. So we would call that an adjacency matrix. So if you have this graph, you have a quantum walk, turns out that a quantum walk on that graph will be able to propagate through that graph at a faster rate. So if you're using a walk to do a search, say, across a graph, a classical walk will diffuse through the graph, kind of like a gas diffusing through a space. But a quantum walk might actually, it'll propagate ballistically, is what we'd actually say. So almost as if it has this momentum behind it, where it just propagates to the other end of the graph far quicker than the random walk. And if we start mapping a problem onto our graph vertices, so say we have a share portfolio and we prepare all of the solutions to possible combinations or choices with respect to our portfolio. So we prepare that as a quantum superposition across a number of qubits.
Mhm.
If we join those qubits together to form a graph structure, we can actually use a quantum walk to get to one of the good solutions in a much faster manner than we could with a random walk.
Wow. Now, where are we at? Where is the quantum world at the moment for divine? I mean, obviously, there's lots of commercial reward for using quantum walks. Are any quantum walks available that end users can now purchase for all the different things we've spoken about? Or are you still writing some?
So where it's very much a case at the moment where you have a bunch of researchers really trying to push the envelope to come up with the algorithm, like the algorithm that is going to do something useful on a current generation of quantum processors.
Yeah, NISQ. On a NISQ.
Yes, NISQ. So near term, is it noisy intermediate scale quantum computing?
Yeah.
I think is the one. Yeah, NISQ. And well, it's not just as simple as calculating our solutions in superposition and then using a walk to find the best solution. We have to also control the walk. And the most established way of doing that is by using a classical optimizer. So we'll set up our system, use a walk, measure the average value of the solutions that we're getting, and then adjust that value and repeat that process until we converge to a solution that is good enough. So we would call these either quantum variational algorithms, or for instance, the quantum approximate optimization algorithm is another name, or the QAOA, or the quantum walk-based optimization algorithm, which is a algorithm that was developed by one of our research group members, Sam Marsh. Now, so these are all using quantum walks, and they're doing it through this optimization process, but it's not easy. We need to figure out what kind of graphs we can use, how we can tune these parameters, and what kind of classical optimizers are even good at that. So now we're bringing in classical optimization, combining that with the quantum computing. So that's two challenges.
When you say classical optimizers, which ones are you talking about?
So in, say, machine learning, we use a thing called gradient descent, where you have a function and you kind of take the gradient and you move in the direction of essentially the slope as it moves down.
Yeah.
We also have a collection of other sort of well-established optimization algorithms like Nilda-Meets, BFGS, and essentially these are algorithms that have existed for a long time that take a function, and it could be, say, a function for optimization of a share portfolio, or it could be a function that's minimizing for the route of, say, a delivery service, and takes this function of a number of variables and basically tries to find some collection of parameters, of variables, that'll lead to either the lowest or the highest value. So it tries to minimize or maximize the problem. Yes. And for people who have done their calculus, they would know that if you have a simple function that you can differentiate, you'll just differentiate your function and then look for points at which that equals to 0. So your critical point. But that's really hard to do, that kind of analytic solution. It's very hard to do with functions of a much higher number of variables, especially functions of really complicated systems. So these optimization algorithms exist to kind of do that numerically. So basically they have an algorithm that looks at the value of the function in a lot of different places in the state space, and then tries to travel from wherever you start off to some local minima. And that's an entire field of research, classical optimization. And it's like an open question as to how we can most effectively use classical optimization to help us tune these quantum algorithms. But while I'm playing up the difficulty, we are actually pretty good at classical optimization. So if we have a function that we can evaluate really quickly, we can use these optimizers to find really good solutions to problems. The only problem is we can't evaluate quantum systems efficiently. If we get a quantum computer containing our problem and we can evaluate that efficiently, then we can combine like the strength of classical computing and the strength of quantum computing into this one hybrid algorithm. And that's really where we're at. So you have a lot of researchers trying to figure out how we can get all of these moving pieces working in such a way that they are the first team to actually solve a problem on a quantum computer in a manner that's more efficient than existing classical methods. And it hasn't happened yet. And it's hard to tell when it will happen because the field is changing so rapidly.
Yes.
But when it does, it'll be very big news. I guess.
Yes, it will be very big news.
There are a lot of algorithms basically that exist, and a lot of people like myself and my other people in the research group and other academics that I've met who are all working and contributing to the development of these algorithms alongside the development of the hardware. So at the moment, you can't purchase an algorithm ordinarily. So there are some startups who have algorithms as part of their IP.
There are some startups doing that, yeah.
There are, but it's very much a new space, and it's hard to tell, until it happens, what the winning horse is, I suppose.
Yes, definitely. But have you heard, I don't want to go off on a tangent, but have you heard of Multiverse Computing, the startup in Chicago, I think? They're claiming to have improved portfolio optimization by 65%. And they say they have a product, and I haven't checked enough whether you can actually take it or not. And
I suppose the question I would ask is, have they got a paper published? Because that's yeah. Ooh, I'll have to take a look at that.
Yeah, please do. I'd love your opinion of it. Multiverse is just one out of a few of them, but they have got a paper on archive.
Mm-hmm. At the moment, there's a lot coming out, and it's a lot of the approaches have a lot of advantages. Some of them have pitfalls. So, for instance, I'm not speaking to their work in particular, but just to give a sense, say, of the challenges that we're up against. You could have an algorithm for optimizing over a share portfolio, which again, so we're doing that by basically encoding our possible solutions into all of the possible qubit sort of configurations. And then we're doing something to that system while we're not looking at it, such that when we measure it, we get a good solution most of the time. So you can have this algorithm that gives a really great speed up, but we have to look at two factors. Firstly, how many qubits does it take? But then also, how many quantum logic gates does it take? So that is like we would use in the classical computing, we have like an OR statement or an AND statement, and we can perform as many of those as we want, one after the other, because the data, just your ones and zeros, stay as ones and zeros.
Yeah.
But if we're doing that quantum mechanically, because we're dealing with this quantum system, every time we change it, we introduce noise, we introduce error, and we have no way of removing that error currently. So you could have this really fast algorithm, but it has what we would call it requires a very deep gate depth or large gate complexity.
Yeah.
And we won't be able to run those algorithms perhaps for 20 years or longer. So that's one of the challenges.
I know that Multiverse is using quantum annealing, so it's not using gate-based. association quantum annealing on a D wave. But look, let's not look.
And that's a whole other thing. So quantum annealing, it's a
Yes.
different model of quantum computation.
Correct.
It's actually related to the quantum walk algorithms, way back when. If that's something you would like to hear about, but it's a very interesting.
I wouldn't mind you telling us a bit about quantum annealing if you could. Or
so I can't speak too much to quantum annealing in particular, but I know that basically the idea, as I understand it, is that we have our quantum system and we want to encode in it we arrange our system such that if we start off in the lowest energy state, so we're talking, a quantum system, we're talking about physical systems. So if we start off in a low energy state, we can slowly change the system so it adiabatically evolves. And so those who have done, say, a bit of physics with your adiabatic evolution, thermodynamics, it's that kind of evolution. So if we very slowly change it, we can slowly evolve the system from one ground state to another ground state that contains our solution. So it contains the information that we're looking for.
Yes.
And you can do that with quantum annealing. The challenge is that we don't know how long that evolution will need to be. And then you need to keep your system coherent. You need to keep the system behaving in a quantum sort of manner during that evolution. Now, what some clever researchers realized, and names escape me at the moment, prime, but they
I'm muting people left, right, and center here. I'm not sure why. It's okay, they're muted. Go on.
Cool. So what the developers of QAOA realized is that we can get this adiabatic evolution and perform this sort of discretization of it called a trotterization. So they say we can get this evolution and break it down into a series of alternating operators. So one of the operators is a quantum walk, and the other operator encodes your solution space into the qubits. So in particular into the phase of the qubits. So you could perform a quantum walk and then this phase shift and then repeat that. And the more you repeated it, the closer you got to the original adiabatic evolution. So basically the lower you could get your energy state, and then the higher the probability that you'd be able to lower your energy state further, that is to say, and increase the probability of measuring a good solution. And that's really like the starting point for a lot of these walk-based, but not all, a lot of these walk-based algorithms. They're actually tied to this early implementation of quantum computing in quantum annealing.
Wow, thank you for that, Edric. I was only following half of it, but it's very exciting. But
so it's an approximation of another physical process that's been abstracted further into something else, because it turns out it does all of these wonderful things. Quantum computing is all interconnected.
Look, definitely. And look, let's get back to what you're doing at the moment. I'd like to know a bit about SpinQ. Have you done anything with that?
I'd be happy to chat about that. Yeah.
I'd be happy to hear you.
Yeah. So UWA and the Pawsey Supercomputing Center are starting the UWA Pawsey Quantum Computing Center, so UpQC. So it's meant to be, or it's going to be an education sort of outreach initiative. And as part of that, together they've purchased a 2-qubit educational quantum computer, which I've been lucky enough to be involved in the setup of the computer.
And this time,
I've got to sit in the room.
You have been lucky.
Definitely.
Good on you.
Yeah, so it's sitting at UWA in one of the labs at the moment. And
fantastic.
I'm running a calibration sort of routine on it at the moment. So it's just running overnight. And I've got to have, I think, a lot of the real experiences you get, working with a computer. That is to say, you turn it on, you're excited, it doesn't work. You figure out why it isn't working. It works. You celebrate the whole process. Except I'm doing it with qubits, which is even more exciting.
That is amazing. So what are your hopes with this SpinQ 2-qubit system? Because if it's 2 qubits, you can entangle them. Or have you done that? Is that easy?
It is. So I think it's within the first, I think, say 5 that have been sold. So we're an early adopter. Yep. It's the only one in Australia. I think UWA is the only university that has like an educational quantum computer at this point.
Oh my God, I did not know that.
Yeah, so it's quite exciting. But they've developed a very nice interface because it's meant to be an educational tool where you can drag kind of like your different quantum gates
over,
onto a visualization of a quantum circuit. So your Hadamard gates,
and the C
X,
naught,
Y, C naught, and build up a program kind of visually. It also lets you interact with the qubits in a more direct manner, where we can send microwave pulses and make measurements on those qubits to alter the superposition if we wanted in a lower level sort of manner.
I don't know whether you can see that from Thomas.
Yes, so they do have the IBM Quantum Hub. I'd say really it's a very small distinction, but it's just that we have the physical hardware sitting in the building. I'm not sure if they have physical hardware.
No, I think they're hooking up to Q. But
I just a shout out to Thomas Crow, who was another example of Perth musicians getting into the sciences. He's now I think a very interesting writer in science communication. So
yes, I think
great
the
to be
three
here,
of us,
Thomas.
We must catch up for a coffee. I had a lovely chat with him before you came on.
Oh, glad to hear.
Yeah, it's great. But did Jingbo pull a few strings or?
Really, I think it's just looking at what's available, and the opportunity came up. So Palsy was willing to put some money into its purchase. So was UWA. And I think together we were able to make this happen. And like, it's really off the bat of a lot of the excitement. Like, we have this kind of tool that'll allow students and researchers to get a sense for how these systems could work. And like, because of the type of quantum computing, so it's NMR quantum computing, where we would be able to actually take, say, a 3rd-year physics student through, like, from starting with Schrodinger's equation, so like the fundamental equation in quantum mechanics. We can start there, define the physical system, and then actually build all of that up to an actual. So you solve Schrodinger's equations for this computer and really kind of get a firm grasp on how quantum computing actually kind of works, from implementation, all the way back to just like the fundamental mathematics. And then for people who aren't, interested in, or, aren't at the point of getting all the way back to the low-level quantum mechanics and the direct notation, you can interact with the machine and you can see the qubits behaving quantum mechanically. You can implement a few famous algorithms, like a Grover's search, for instance, which is a walk over a graph, is one where you can look at that one and actually see it optimize a system, like where it finds a marked node. So it's an algorithm where we have a complete graph, and in that graph we want to find a single node that's marked 1, everything else is 0. There's an efficient quantum algorithm that'll carry out that search, and you can run that on SpinQ and actually see it play out. Actually, you read about these algorithms, you simulate them, but it really is something else actually carrying it out for real and being
Oh,
there in the room.
definitely.
Yeah, it's hard to almost quantify. I didn't realize I'd be that excited, until like I was sitting there and I was actually
Yeah.
working with it.
What a great insight. I've never had the pleasure. Mind you, I'm not a programmer, so I don't get involved with that. But I can understand what you're saying, and when you're actually doing it, it's something else. But could you elaborate more on the microwave pulses? Because you've got your quantum gates, which are basically behind. So you've got your high-level programming where you just drag them down. Behind them, they are represented by matrices. And then behind that, so the physical qubit is manipulated by microwave pulses.
So it depends on the architecture, but this particular type of quantum computer is it's an NMR quantum computer, so nuclear magnetic resonance.
Yeah.
And this was actually an early platform for quantum computation, and it's not thought to be very scalable, so an early caveat.
Yeah.
But one of the nice things about it is we're able to do room temperature computation. And the way it achieves computation is by actually using a sample of one particular type of molecules. So one particular type of molecule. So we've got 10 to the 15 of this dimethyl phosphite. And
okay, can you spell that?
So we've got di, methyl, and then phosphite. So PHOSPHITE.
Oh, Thomas has spelled
it. Thanks, Thomas.
Yeah, that looks about right. I just need to look that up. Okay.
And this type of molecule has a couple properties that we really care about, and that is it has a hydrogen atom, which is bonded to a phosphorus atom that in physics we would say they are both spin 1 systems. So we talk about electrons having spin, so spin up, spin down.
Yeah.
Nuclei in molecules can also have spin. So this hydrogen has a spin up, spin down. Phosphorus also has a spin up and spin down. And if we think about our definition of a qubit, so what is a qubit? A qubit is a quantum system with 2 states. And we often map that to a spin system, spin up, spin down. So both of these nuclei inside this molecule can function as qubits. That's cool. But not only that, they can sort of function as qubits, and they have very different resonant frequencies. So that's to say, if we want to flip the phosphorus from spin down to spin up, we can use one frequency. But then if we want to do the same for the hydrogen, we have to use a microwave frequency, so a pulse of energy, that is hundreds of hertz different. So it's like a very, very different frequency. So that's great, because now we have 2 qubits that we can individually address. So we can manipulate them independently. But that's not all. They're connected in a molecule. So they influence each other. So we have 2 qubits that we can address individually that interact with each other. So now we can do quantum computation.
Exactly. Wow.
And
it sounds very like NV-centered.
NV-centered?
Yeah, nitrogen vacancy, which quantum brilliance are using. They have I don't know whether you know much.
It's not quite the same sort of physics.
No.
It's like, we could think about molecules having, say an atom having orbitals. So the Bohr, we'll say this Bohr model of the hydrogen atom, where we have our sort of shells, and each, as you go further out, your electron's getting more excited.
Yeah.
There's like a finer structure in molecules where you can think about how excited an individual atom in a molecule actually is. So
Electron, do you mean?
Yeah. So we're thinking about an electron in a, well, no, we're thinking about a nucleus in this case, in an atom that also has spin, and it can be kind of pushed up and down energy levels. So we'd call this it's the hyperfine structure of a molecule. So we're not just with molecules of energy levels. We can excite them, then we can get even deeper and talk about the fine structure. But really, 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 a really nice thing about it is we can model it to a pretty high, amount of precision, just as two qubits coupled to each other, and we can ignore the rest of the molecule to a large extent. So it's actually a really simple system from a mathematical and computational standpoint, once we've done all of the work to figure out the resonant frequencies.
Now, Thomas, I was about to ask a question. Why isn't it scalable? Have you got that?
Yeah, so I was asking if it's like limited because of the application of EM radiation to change different elements. Yeah, so if it's due to the our need to have a different resonant frequency for each of the atoms.
Did you want me to just ask it so that it can be recorded?
Yes, thank you.
Thanks,
that would be great.
Yes.
I should have invited you to. Please do.
So I was basically just asking, from the way you described it, it sounds like the way you're able to alter the qubits is applying a specific frequency of radiation to change the energy level of whichever atom you want to change the rotation of or the spin of. So is the reason it's not scalable is because you would basically need a different atom for every single qubit that you wanted, because there's no way to specifically target a single atom if there's multiples of it, if that makes sense?
I think that would be a factor, but I think it's largely, I think like as the size of the molecules kind of grow, I think it gets harder to have a system where we get the kind of interactions that we would need between those systems. So if we're talking about like an interaction between two qubits now, which are like several bonds removed, I think that is actually the main factor that is contributing to a lack of scalability, because you can get molecules where a lot of the different atoms have fairly different local kind of conditions. You could maybe probe them individually if you had an accurate enough source of microwave radiation. But I think the scale, like the size of the molecule, starts becoming a challenge earlier on.
Once it gets too big, you're basically entering the realm of like classical physics. Is that fair to say?
Kind of like you're struggling against the structure of the molecule in terms of how well you can kind of couple these systems together, like how well you can get the qubits to talk to each other. And like that's like one of the main challenges in current sort of superconductor-based quantum computing, say with IBM systems. So we might have 100 qubits, but we're not able to couple or entangle each qubit with every other qubit because of the actual physical layout of those qubits.
Yeah.
So, and in that instance, they're engineering the layout carefully to improve that property.
The quantum topology or whatever.
It's called. The quantum topology. Yeah. Thank you. The topology of our qubits. It's a great question. Thanks.
Wow, believe it or not, it's 7 o'clock, Edric.
Wow.
Wow, indeed. Honestly, I was looking and I was thinking, okay. I was looking, thinking, and we probably got 20 minutes to go. I'll ask for some questions soon, but oh, wow. Thank you so much. You've covered an awful lot there. It's unbelievable. Well done.
It was really nice chatting. And Yeah, thanks for having me along. It's a
Yeah.
lot of fun to talk about this.
Oh, I think we should have
and
another one
I'd
if
be
that's all
very
right with
happy
you.
to.
I
I
mean,
think, yeah.
No, you go on.
I just wanted to mention that so the QUISA research group has a website. So that's quisa.tech. So QUISA.tech, and we post our meetings on there, topics, papers, so on. So that's a good place to find about the work that's being done in Perth. I also have a GitHub where I have open source software packages that I've developed for performing quantum simulation. So if you search for my name with a dash, GitHub, that should show up. And if you're, for any students who might be watching this, high school, I know that UWA has recently started a frontier physics program. So that's a 4-year master's, undergraduate through to master's program where you get to start working in quantum mechanics from first year. So there are my plugs. Like if anyone watching this is curious, please take a look there and feel free to reach out.
Absolutely, that was wonderful. Do we have any questions from anybody here? I mean, we just covered so much.
If we talk again, I'd love to go through some of what it's like to do research in the day-to-day.
Yeah, well, let's definitely arrange that, because I know I learned an awful lot. Now I'm going to